and I'm here today to talk about the subject of math and music. So why are they related? You're probably asking. Math on one hand is very rational and it's reason, and you have equations, numbers, fractions. It's very annoying to most people. But music, on the other hand, is very beautiful, it's passionate, it's enjoyable when you listen to it. So why at all are those two subjects, who are vastly different, related? Well, first of all, I'm going to tell you that if they aren't, I wouldn't be standing here. But essentially, math is the law of nature. It's present in everything. Math is present in the architecture of this room. It's present in your human body. It's present in the mechanism of this projector and this keyboard. So simply put, math rules. And math is also present in music. But how? Let me just start by asking you this question. Does anybody know who this guy is? Any guesses? Shout them out. Close. Close. He is Greek. So, all right, so here's a hint for those of you who don't know who it is. So this is hopefully well known to all of you in the room. It's called the Pythagorean theorem, which they so creatively named after the man who discovered it, the Greek mathematician Pythagoras. And if you were really into watching Disney cartoons when you were really young, you might remember this episode. So this cartoon is called Donald Duck in Math Magic Land. And look at this guy right here. That's Pythagoras. He doesn't look so similar with the picture I just showed you, but it's okay. Take a look at the instrument he's playing. That's called a lyre. And see how the strings are different? The length of the strings are different on the instrument? And that is how they are able to produce different pitches. So this is how it works. And here's the story. So one day, Pythagoras was taking a walk casually around town, and then he happened to walk by a blacksmith shop. And he noticed that when the blacksmiths hammer the iron, they produce different pitches. And he thought that was because of the different weights of the hammer, that when it strikes the iron, it produced different sounds. So he ran back home, very excited, and performed an experiment. He tied different weights onto strings and plucked them. And surprisingly, well, not really, but they produced different pitches, just like they did at the iron shop. And this is what he found. Oops, not that. So if you have a piece of string, like this one right here, and you divide it in half into this one, that produces the interval of an octave, and it sounds something like this. So I think that sounds very familiar to most of you. And the first two notes of that song, that's an octave. And in music, we call that the same note, but just played in different registers. And why do they sound so similar? It's because of this very simple 2-to-1 ratio, that it fits very nicely. So it's very nice to hear for the human ear. And if you divide the string into 2/3, that produces the interval of a fifth. And this is what it sounds like. So the first two notes of the theme song to Star Wars is a fifth. And that's also a very nice sound. It's also because of this ratio of 3-to-2. And if you divide the string further, then you have this string right here. It's 3/4 of the original string, and that interval is a fourth. And it sounds like this. The first two notes to the wedding march is a fourth. So let's dive deeper and look at the physics So see, when you pluck a string, it produces an oscillation throughout the string. And that can be expressed as a sine wave. And this is what a sine wave looks like. So say this is a graph of a sound wave of the first bass note of of the original string that we just saw, this one right here. And that's the graph of it. Now you have its wavelength. You have an octave. The red curve is the note that's an octave above it. And it goes through 2 cycles, while the blue curve goes through 1. So the ratio of 2 to 1. And now divide the wavelength further. And you have this purple curve, this one right here, and that's a fifth. The red curve goes through 2 cycles, while the purple curve goes through 3. So that's the ratio of 2 to 3. And now flash forward a few thousand years. Now we know the piano as divided into 12 equal intervals, which is known as the equal temperament scale, and it sounds like this. And the octave is divided into 12 equal steps. But it doesn't quite work like 2 divided by 12. See, in sound waves, it's not that the strings are divided into different lengths. It's that they're divided into different ratios. And that magic ratio number happens to be 2 to the 12th root. And it wasn't until mathematicians were able to take 2 to the 12th root that musicians can tune their instruments according to the equal temperament scale. And guess who got really excited? Bach. He got so excited that he wrote a whole book, divided into 2 sections, whole book on all 24 majors and minor scales. And each set is made of a prelude and fugue. So now I have 48 new pieces to learn. Thanks, Bach. But the reason that the equal temperament scale is so cool is that it allows musicians to play any song on any key, and they would sound the same. So Bach's prelude in C major is one of my personal favorites. It's also the first piece of the book. And it's one of my personal favorites of the Well-Tempered Clavier. And I will play a little bit of it, and some of you might recognize it, but here it is. So you might notice that there are different melodies, and they're all made of broken chords, like this one, which is the first measure of the prelude in C major. And the different chords are basically the building blocks of the song. And look at the first measure. It's a very nice C major chord. And that sounds very pleasant to the human ear to hear. But why is that? So when you play the chord on the piano, these are the notes that you play. So instead of going note to note, you skip each note. And that is what you get. That is what you call a triad. And look at the sine curves. This red curve is the root note of the chord, C. And the blue curve is the fifth, which is G. And the green curve is the third, it's the note E. And the red curve goes through 2 cycles, while the purple curve goes through 3, hence the ratio of 2 to 3. And the green curve goes through 2.5. They all intercept at this magic point right here and fit very nicely together. And that is what we call a consonant, something that is that fits together very beautifully, and it sounds very pretty to the human ear. But recall the second measure. which sounds like this, if you forgot. It's still a very beautiful chord, but it doesn't sound as well spaced out as this chord right here. The reason is that you have this note, which is a C, and this note, which is a D, played together. This is called a D minor 7th chord. And this sound, well, it's not necessarily a bad sound, but it's very, you can hear the sounds are running into each other when they're getting to your ear. And this is why that produces a clash sound. So take a particular look at the orange curve. Well, the other 3 curves all intersect very nicely at this point right here, but the orange curve doesn't. It kind of intersects the other 3 curves here. And that doesn't fit very nicely. That is why that the D minor 7th chord doesn't sound necessarily as nice as the C major chord. But why does this matter? Well, to be honest, it doesn't. It only matters to me because I happen to love both music and math. And being able to find out that there are very deep connections between those 2 subjects has allowed me to look at music and math in a different way. So what I think is really cool about this is that while music is very beautiful and passionate and emotional, it has its principle lying in math, a subject that's completely different. And math, something that's very rational, and you can call it boring to some extent, but it underlies the very important, the very fundamental principles of music, which is very beautiful and emotional. And that discovery almost made me think, almost made music sound more beautiful to me. And take a look around you. There are very deep connections between everything. And I think that's the beauty of this world. Thank you.